Homework from last night, page 647, number 1 to 2, 5, 7 to 14. We need to go over 6 questions, it looks like here, 1, 8, 9, 10, 13, 14, starting with number 1. 2 ways that electromagnetic radiation is detected. We talked about one of them yesterday, and this is the kind of the scientific experimental way of detecting electromagnetic radiation, but there's other ways as well that are somewhat less scientific or somewhat less experimental. What's the one that we talked about yesterday? Heinrich Hertz spark gap apparatus, right? He experimentally detected, that is, electromagnetic radiation by accelerating electrons across a gap, a spark gap. And as they accelerated across that gap, if they produced EMR, then we should get an electric current induced in the antenna. Sure enough, there was a current induced in the antenna, changing electric and magnetic field that caused it, caused by that accelerating charged particles. So we detect electromagnetic radiation with an antenna, right? At least that's how Hertz detected it. How else can we detect electromagnetic radiation? Open up your eyes. Literally, open up your eyes. How else can you detect electromagnetic radiation? Open up your eyes and see something, because visible light is electromagnetic radiation. Now, that's not some kind of experimental way of detecting EMR, but we are literally detecting EMR in the retina of our eyes as the light goes through the lens and focuses on the retina of our eyes. Turn on the radio, listen to the hockey game or the baseball game on the radio. You're detecting electromagnetic radiation with an antenna. All right, number 8. Number 8 says, a high voltage spark gap produced sparks with a frequency of 2500 hertz. What's the frequency of EMR observed at the antenna located nearby? Well, what is it that's causing the EMR? It's the spark gap, right? It's the frequency at which the electrons are accelerating through this gap. Well, if they're accelerating through this gap, the frequency at which they're going through this gap back and forth is 2500 hertz, then the frequency of the EMR they generate is going to be 2500 hertz. So that's it. Whatever causes it has the same frequency as whatever is caused. So it's the spark gap at a frequency of 2500 hertz that causes the EMR at a frequency of 2500 hertz. Number 9, what properties need to be considered when choosing the material to build an antenna for our radio receiver? What materials need to be, or what properties need to be considered? There's only one really important one that I can think of. Conductivity. Yeah, it's got to be a conductor. Somebody this morning said, okay, I get that it has to be a conductor. Does it have to be ferromagnetic as well? No. No. When we talked about electromagnetic induction in our last unit, or generator effect, whatever you want to call it, we had a wire, we had a magnet, and you move one of them, you generate a current in the wire. The wire didn't have to be ferromagnetic. This is the same thing, except that we're not moving the wire or the magnet. This time we're changing the magnetic field strength. Changing magnetic field strength, sinusoidally changing the magnetic field strength, okay, inducing a current. Well, it's just got to be a conductor. It doesn't have to be ferromagnetic at all. Number 10, if the magnetic field lines held within a closed path are constant and unchanging, will there be an electric field along the closed path? Yes or no? If you have a magnetic field that is constant, will that make an electric field? Who says yes? Who says no? All right. 2 of you said no, and none of you said yes. Good news. The unanimous vote for no is correct. Okay, all 2 of you that said something are correct there. No, there isn't an electric field produced by a magnetic field. Now, there could be an electric field potentially, but it's going to be caused by something else, not caused by the magnetic field. In order to cause an electric field, the magnetic field has to be changing in magnitude. Number 13, Describe how an antenna is affected by an EM wave. We kind of alluded to this before. Antenna is affected by an EM wave by having a current produced in it, right? It's electromagnetic induction. A changing magnetic field can induce an electric current in a conductor. And the antenna is just a conductor, so you get a current produced in it. And finally, number 14, describe what method used to produce EMR with a known frequency. Anybody have one for that? Yeah, great. All right, a spark gap apparatus, sure. Something as simple as an alternating current. The current that goes through the electrical wires in your wall goes back and forth at 60 hertz. That produces really, really low frequency radio waves, 60 hertz. That would be a known frequency, right? If the current is going back and forth at 60 hertz, then that would be the frequency the EMR produced as well. Think like electric current, like regular electric current produces radio waves. Yeah, it's just really low intensity radio waves. You ever find yourself driving out on the highway or out on the road and you're listening to something on the radio and all of a sudden you drive under a power line, like you know, a high voltage power line, and you find the radio cuts out? You ever notice that? Yeah, it does sometimes, not always, but it does sometimes. And the reason it does that is because the current that's going through those wires are producing radio waves, and they're interfering with the radio waves that you're trying to detect from the radio station. And when you drive past it, it goes back to normal because there's no interference anymore. Same thing happens, same thing potentially can happen with the electric current in your house, except the intensity of the EMR that's produced is much, 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 much smaller. So small that realistically, it's probably not going to interfere with anything, right? Today, I want to zip forward and talk about the speed of electromagnetic radiation. We already established that the speed of EMR is 3 × 10⁸ meters per second in a vacuum or in air. But today we want to talk about how exactly we measure that speed of light, or at least how historically we measured that speed of light. We're going to go way back to Galileo. Galileo set up an experiment with an assistant. Looked something like this. Galileo and his assistant took 2 hills, 1 kilometer apart from each other. Galileo stands on one of the hills, his assistant stands on the other hill. Galileo has a lantern, like a lantern like that has a little flame in it, right, that'll shine light. So we'll put a lantern on this one. His assistant has a lantern that shines light as well. But right now, both of them are covered up. So neither one of them can see each other's lantern. Galileo has some sort of primitive way of keeping time. We'll call it a stopwatch, but it's not literally going to be like a stopwatch that we have on our wrist or on our phone now. Okay, but the idea is the same, that we can measure time with it, some primitive way of measuring that time. So here's how the experiment goes. Galileo on one hill with his lantern covered up with a sheet, his assistant on another hill a kilometer away with his lantern covered up with a sheet. Galileo stands there, uncovers his lantern, and as soon as he does that, he starts a stopwatch. So he starts measuring the time as soon as he uncovers his lantern. That light travels towards his assistant on the other hill a kilometer away, and then when his assistant sees it, he uncovers his lantern. So I uncover my lantern, I'm Galileo, I uncover my lantern, I start the stopwatch. Okay, the light goes towards Dom over there, who's going to be my assistant. He sees the light, he uncovers his lantern. Then that light travels back to me. When I see the light that was uncovered at my assistant's hill or Dom's hill, then I stop my stopwatch. So what I'm doing here is measuring the time with my stopwatch that it takes the light to go from my hill, as soon as I uncover the lantern, right, from my hill to Dom's hill, and then he uncovers his lantern, so from Dom's hill back to my hill. In other words, I'm measuring the time that it takes the light to travel a distance of 2 kilometers. Now, That provides us with a pretty simple way of measuring the speed of light. The distance that the light travels is 2 kilometers. The time that it takes the light to travel 2 kilometers is whatever it read on my stopwatch, right? There's a problem, though. There's a problem. His number that he got for the speed of light there was way off. Like not even remotely close to the actual value for the speed of light. Why? What's wrong with the method that we just used? It seems logical. In fact, it is logical. In theory, it's all good. But why doesn't it work in practice? Yep. Yeah, the time that it takes the light to travel 2 kilometers, it's almost instant, right? Almost. Not literally instant, but almost instant. The time that it takes me to start and stop the stopwatch, the time that it takes Dom to uncover his lantern, the time that it takes me to uncover my lantern, those times are all significantly bigger than the time that it takes the light to travel 2 kilometers. So even if I get a time, it's going to be so far off of the actual time that the speed that I calculate is going to be meaningless. Even if I did happen to get a number that was somewhat close to the accepted value for the speed of light, it would be purely coincidence. So we need to come up with a better way of measuring the speed of light. Again, this is not a bad idea, except that to make this work, the distance involved would have to be much greater than 1 kilometer. In fact, it would have to literally be an astronomical distance, a distance that was so big that reaction time wasn't nearly as significant. Well, let's give you a better way of measuring the speed of light. Michelson performs an experiment, or an experiment. Michelson performs an experiment to find the speed of light that worked much better, got us a value that was much closer to the accepted value for the speed of light than did Galileo. The setup of this in some ways is similar, but in some ways is quite a bit different as well. Okay, let me give you the basics of it. Michelson has 2 hills as well, Mount Wilson and Mount San Antonio, but instead of being 1 kilometer apart, they're 35 kilometers apart. Now, that extra distance doesn't make much of a difference. If you've got Galileo on one hill, 35 kilometers away from his assistant, and you uncover the lantern, then you uncover the lantern on the other one, it's not going to make any difference, right? Even though you're talking 35 times the distance, the reaction time is still much, much too big to get a reasonable value for the speed of light. So what Michelson does is designs an experiment to avoid having to count on human error. So here's what happens. On Mount St. Wilson, Michelson has a light source. Okay, so he directs that light source at this octagonally shaped object that has a mirror on each face. So it's got 8 sides, an 8-sided mirror, we'll call it. He directs a beam of light towards, let's say, side 4. Light reflects off of side 4 and strikes, as it reflects off of side 4, comes down here to Mount San Antonio, 35 kilometers away, reflects off of another mirror, a mirror that is, sometimes you see it drawn as a flat mirror like this, sometimes you see it drawn as a curved mirror like this, doesn't really matter. That light reflects off of that mirror, comes back here, reflects off of mirror 6 or side 6, and then gets observed by somebody over here. We've done nothing right now to measure the speed of light. Okay, understand that. Okay, right now we've directed light at a mirror, it's reflected, it's been observed. We haven't measured anything right now. We got to do something to this to measure the actual speed of light. Here's what we're going to do. We're going to start spinning this mirror. We're going to start spinning it on its axis. So counterclockwise, or sorry, clockwise, like this. If I spin it, if it's spinning as as the light is directed from this source, maybe the light reflects like this. Okay, maybe the light reflects off of site 4, comes back down here to Mount San Antonio, reflects back. But watch what happens if during the time that the light went from site 4 to Mount San Antonio and back up to site 6, watch what happens if the mirror was spinning during that time. Maybe now the mirror hits, or the light when it comes back doesn't hit site 6 and reflect and get observed by the observer. Maybe it hits site 5 and bounces up like this. Doesn't get seen. So the light doesn't get observed here. The mirror is rotating. The light reflects at the wrong angle because the face of the mirror is at the wrong angle, such that it doesn't get observed anymore. But we want it to get observed. It was easy when the mirror was stationary. Now that the mirror is spinning, the mirror has to be spinning at just the right rate, such that one of the sides over here is at the right angle, so that the light ends up being reflected into this person's eyes again. So, what does it got to look like? Well, if the mirror has spun that much in between the time that it took to go from Mount Wilson to Mount San Antonio and back again, then it's not going to get observed. But if the mirror has rotated that much, then all of a sudden this light reflects at Mount San Antonio back here to side 5 and gets observed by the observer. Now, when the mirror was stationary, it was reflecting off of side 4 and then side 6 into the observer. Now, maybe it was reflected off of side 4 right here. That was side 4 right when it hit that side. But now, as it's spinning, reflects off of side 5. What I'm saying is that if side 5 has come in to take the place of side 6, in other words, if the mirror was like this, when it reflected at Mount Wilson the first time, and then it was like this when it reflected at Mount Wilson the second time, then that means that the mirror, during the time that it took the light to go from here to here to here, 70 kilometers, the mirror has made 1/8 of a rotation. You see that? This is where the mirror was when it reflected the first time. This is where the mirror is when it reflects the second time. It has to have made exactly 1/8 of a rotation in order for the light to be observed by the observer. So the mirror has to either be at rest for the light to be observed by the observer, or it has to make 1/8 of a rotation to be observed by the observer. Does that make sense? If it's made like somewhere in between 0 and 1/8 of a rotation, then the mirror is going to be like this, and the light's going to be reflected in the wrong place. It's not going to be observed by this person over here. So how does that help me to find the speed of light? Well, the speed of light can be found by using the equation v is equal to d over t, just like Galileo used. The distance that I would use here in this case would be 70,000 meters. 35 kilometers there, 35 kilometers back, and then convert it to meters. The time that it takes, we don't know. We don't know what time it takes. How long does it take the light to go from here to here, back to here again, that 70-kilometer distance? We don't know. We don't know. But what we do know, a little bit easier than measuring that time with a stopwatch, is the frequency of the rotating mirror. Usually it's going to be in the range of 500, 600, 700 hertz. That's a high frequency, right? 500, 600 cycles per second. That might be hard to measure, but it's going to be a lot easier to measure than it is to measure the time that it took the light to travel 70 kilometers, measuring it with a stopwatch. If we know the frequency, or we can find the frequency, then we can find the period, the time for one complete rotation. And given the time for one complete rotation, we can find the time for 1/8 of a rotation, which is really what we want here, right? The time that it took the light to travel 70 kilometers is the time that it took the light, or the mirror, I should say, to make 1/8 of a rotation for side 5 to come in and replace side 6. So if I know the frequency, I can get the period, If I can get the period, then I can get the time for 1/8 of a rotation. And if I can get the time for 1/8 of a rotation, I can divide 70,000 by the time for 1/8 of a rotation to give me the speed of light. Okay, what makes this one so much better than Galileo's method? It's right back to what Max said before about Galileo's method, right? What makes this one so much better? We don't have reaction time here. There's no human being involved in this. Right? We have to know the frequency of the rotating mirror. And maybe we're off a little bit on the frequency of the rotating mirror, but we're not going to be off nearly as much on the frequency of the rotating mirror as we're going to be on the time that it took light to travel 2 kilometers, because we don't have reaction time involved in measuring the frequency of the rotating mirror. That make sense? Because reaction time is a non-factor in this, we're going to get a much, much better value for the speed of light. All right, I want to do an example here. Page 650. It says the set of rotating mirrors in Michelson's experiment was rotating at 533 hertz. Remember I said it usually, not always, but usually in the 500, 600, 700 range. 533 hertz. The curved mirror was located, that's the curved mirror on Mount San Antonio, the second hill, located 35 kilometers away. We want to find the speed of light. So the light goes, reflects off of the 8-sided mirror, off of the curved mirror, or I had it drawn as a flat mirror. Back here, gets observed by the observer. This is 35 kilometers. So the total distance traveled is going to be 70 kilometers. The frequency is 533 hertz. Listen carefully, because for once in Physics 30, we have a question that can be solved by a recipe. In Physics 20, we have that a lot, right? Hey, here's a recipe for solving these problems. It's going to be the same pretty much all the time. In Physics 30, we don't have recipes, right? We have to think hard about questions that we're doing, figure out what's going on and think hard about them. This is a recipe, and this recipe works all the time. Okay, if you want a little bit of a break from having to think real hard, okay, this is your chance. You got to understand this, but in the end, if you do, you can do the same thing every time and get the right answer every single time. Here's what you do every time. Write down these two equations. V equals d over t, t is equal to 1 over f. Every single time. Every single time you see one of these problems. And by the way, I'd say that this appears on your diploma exam about 85 or 90% of the time. You're almost guaranteed to see one of these questions on your exam. Almost guaranteed. If you do, or when you do, write down these two equations. And then sub in numbers. Sub in what you got. I don't know what speed is, that's what I'm trying to find. D, yeah, I know what that is. It's 70,000 meters, because the light travels 70,000 meters during the time for 1/8 of a rotation. T, I don't know what T is. Which is too bad, because I want little t, right? If I want to solve for V, I need little t. Here's the thing. You plug numbers into these two equations, the first thing that you're going to solve for every time is going to be a time, either big T or little t. But here's the frustrating thing about it. Whatever time you solve for first is not the one you want. We want little t so that we can find V, but I can't get it. So I got to get big T. Let's get the value of big T. Remembering, of course, that it's not really big T that I want. It's little t that I want. That's okay. Get what you can get. 0.001876. That's the time for one complete rotation of this mirror. That's not what I want. If we go back to the picture here, you know that the mirror didn't make one complete rotation during the time that it took the light to travel 70 kilometers. The mirror didn't do this during the time that it took the light to travel 70 kilometers. The mirror did this during the time that it took the light to travel 70 kilometers. The mirror made 1/8 of a rotation. If we've just solved for the time for one complete rotation, then let's divide that by 8 to get the time for 1/8 of a rotation. I get 2.345 times 10 to the minus 4. That's what we want. Remember, you're always going to solve for a time first, but it's never the one you want. If you get big T first, get little t by dividing by 8. If you get little t first, then you're going to need to get big T. Multiply by 8. Take this little t, the time for 1/8 of a rotation, plug it in here. 70,000 divided by 2.345. And we'll see what we get here. 2.98 times 10 to the 8. You get a number that says 2.98 times 10 to the 8 meters per second for the speed of light. You can be pretty confident that you've done that right. That is pretty close to the accepted value for the speed of light. So regardless of whether you're solving for the speed of light or they give you the speed of light and you have to find the frequency of the rotating mirrors, you're always going to start off the same way. Write down those two equations. Sub your numbers in. And when you do sub your numbers in, you're going to solve for either little t or big T. If you've got big T first, like we did in this example, then you need to get little t by dividing by 8. If you've got little t, then we need to get big T. And we're going to get that by multiplying by 8. So write down your equations, solve for one of the times, big T or little t, get the other one by multiplying or dividing by 8, and then finish it off. Simple as that. Now, little word of caution. Sometimes we see a problem involving, they say, a Michelson-like experiment. Maybe it's a 12-sided mirror. Well, how would that change things? You would multiply or divide by 8. You would multiply or divide by 12, right? Sometimes you might see a problem where the distance in the Michelson-like experiment isn't 35 kilometers. Maybe it's 10 kilometers. That's okay. Just make sure you include the distance that's used in that particular question. Otherwise, it's going to work exactly the same way. Look at number 1. It says students use a 12-sided set of rotating mirrors. That's the first thing that I noticed, actually, because most of these questions are 8-sided. Michelson's experiment was actually 8 sides. So when we're dealing with something other than 8 sides, find what happens is we often get in that habit of just using the number 8. Okay, we want to draw attention to the fact that it's not 8 sides this time, it's 12 sides. Yep. Similar to Michelson's experiment, he determined the speed of light to be 2.88 times 10 to the 8. Mirrors are located 30 kilometers. Strange units there. A number that's not normal either, because usually it's 35 kilometers. From the fixed mirror, what's the frequency of rotation if 1/12 of a rotation occurs before the light returns? Well, we know that we start off every question the same way. V equals d over t, t is equal to 1 over f. Let's write down what we have, or let's sub in what we have. This time we know the speed of light, 2.88 times 10 to the 8. The distance is 60,000 meters. And look at that, I'm able to solve for little t. That's the time for 1/12 of a rotation. But remember what I said? Whatever time you get is not the time you want. If you get big T, then you want little t. If you get little t, then you want big T. That's okay. Let's get little t, and then we'll worry about big T later on. Let's say little t is going to be 60,000 divided by 2.88 times 10 to the 8. Gives us a time of 2.0833 times 10 to the negative, I think it was negative 4. Yeah, 10 to the negative 4 seconds. Remember, that's the time for 1/12 of a rotation. We don't want the time for 1/12 of a rotation. If we get little t, then we want to get big T. So let's multiply that. Listen, people have trouble remembering, do I multiply or divide? If you've got a little thing, little t, and you want a big thing, big T, then you multiply. You multiply to get something bigger. If you've got little t, you multiply to get big T. If you've got big T, you divide to get little t. So let's multiply that by 12 to get big T here. And when I do, I get 0.025 seconds. Remember, I got the time for 1/12 of a rotation. I want the time for one rotation. Let's sub that number for one rotation, 0.025 seconds, in for big T, solve for F. F ends up being 1 over 0.025, which I think works out to be 400, I want to say. Is it 400? How many people got that? Good. Good. Question number 2, I'll let you guys work on question 2 and 3 for another couple minutes here. Question number 2 you're going to find is real similar to question number 1, except they don't give you a speed of light. They're asking for frequency again, but they're not giving us a speed. What are we going to do? If we're solving for frequency, we have to have a speed. If they don't give us a speed, then we have to assume that the speed is what it really is, 3 times 10 to the 8. So you're going to assume that in question number 2. And if you do that, you're going to find that the questions are virtually identical to question number 1. All right, let's get back at question 2 and 3. And then if we need to, we'll take a look at another one in a moment here. If we're good with those Michelson problems, we need to be good with them because we know that there's an 85 or 90% chance we're going to see one on our diploma exam. We know that there's a 100% chance we're going to see one on our unit test. We also know that there's a 100% chance we're going to see a Michelson question, not on our quiz tomorrow, but on our next quiz after that. So we know we're going to see it at least twice for sure, and probably 3 times on tests that matter. We're okay with those. Then we're going to move on to one more type of question involving light speed. Okay, we've established how to find the speed of light now with Michelson's experiment. Now let's use that speed of light to measure something or to calculate something. So here's the question. So the distance from Calgary to Regina is 800 kilometers. How long does it take light to travel from Calgary to Regina? If the wavelength of the light is 600 nanometers, what's its frequency? So 2 questions here. How long does it take light to travel to Regina, and what's the frequency of the light? Well, I know that Regina is 800,000 meters away from Calgary. And I know that the speed of light is 3 times 10 to the 8 meters per second. So let's say 800,000 divided by 3 times 10 to the 8, 2.67 times 10 to the negative 3. Do we expect to get a small time here? Yeah, of course we do. When we introduced this unit, we said that light could travel approximately 25 return trips across Canada in 1 second. If you can make 25 return trips across Canada in 1 second, it's not going to take very long to go to Regina. 2.67 times 10 to the negative 3 seconds. What about its frequency? Let's use the wave equation that we learned in physics 20 for that. F is equal to V over lambda, 3 times 10 to the 8, divided by 600 nanometers. A nanometer is 10 to the minus 9 meters. If you're not sure about that, then check your data sheet. It tells you. Just replace the n with 10 to the minus 9. That's not scientific notation, but that doesn't matter. It's not a final answer. 600 nanometers or 600 times 10 to the minus 9 meters. Do that math, it works out to be 5.0 times 10 to the 14 hertz, which if we have to identify the type of EMR, we're going to say that's visible light. I'm going to give you some questions for homework. right now. Those questions are going to be page 652, number 1 to 2, and 6 to 11. Tomorrow, you're going to be given a couple relatively short worksheets. One's going to be on the Michelson experiment. One's going to be on this type of thing that we just did. I want you to work through those after your quiz. And then, depending upon time, we're going to show you a 20-minute podcast on something else that you're going to do some work on as well. Okay, but for sure, depending upon time, we've got a quiz, we've got a little worksheet on this, and we've got a little worksheet on this, just as a bit of practice. And we'll take a look at those on Thursday when I come back.